Right, episode 9. We're into shocks part 2. What we're going to do in this episode is put RC crew chief to work a little bit and see what we can learn about how to adjust handling using our shocks. So let's get to it. We'll go back and start at the main page. So if you're following along with the trial version of the program or the full version, just select the 1/8 scale four-wheel drive truggy from the list. That's the one we're going to be using in this episode. If you do not have the trial version of the program installed and you would like to follow along, just go to the RC Crew Chief website and download it. There is no charge. Okay, so let's go into setup and click on our shock spring shock and ARB tab. So what we're going to be talking about is our damping ratio. And first thing to look at here is the damping ratio that's displayed here is calculated at the ride frequency of the suspension. So this is essentially the natural frequency or the natural oscillation rate that the suspension would bounce at with no damping in the system. So this damping ratio is calculated at that frequency. The damping ratio, as we've shown and will show, changes quite a bit over the range of speeds that the shock can be exposed to the velocity of the piston moving in the shock body. Okay, so first up, let's just have a look at temperature. This is one thing that may get overlooked quite a bit. So let's just see what happens as we change temperature. So say we're going from a normal spring day to a summer day. So our temperature's gone from 20 C to 30 degrees C. So right there you can see we have a very significant change in damping ratio. So to recover that, we would have to adjust our shock oil. So here, shock oil, let's try 700. Let's go up 100 points and see what happens. Okay, that's pretty close. Maybe we have to go up another 50 points. There we go. So we have to go up 150 points in CST rating of our shock oil in order to get the damping ratio to be the same. If we were going the other way and we were down at 10 degrees C, then we would probably have to go down 150 points. Let's go down 150 points. Well, maybe we don't have to go down quite as far. Let's go down 100 points. Okay, so somewhere between 100 and 150 points to get our damping ratio back where we originally had it when we were racing at 20 degrees C. Okay, what do I want to talk about next? Next, let's look at our shock angles. So when you're changing your shock angles, you're not really changing the relationship between the shock damping and the spring. That's staying constant. What you are changing is the geometry of the shock relative to the chassis itself. So you could consider that the damping is staying constant. You will see here as I start clicking through this that it will change a little bit. So let's go and stand our shocks up. So that's going to change a whole bunch of things. Changes our ride stiffness, ride frequency, stiffens up the roll stiffness, and it also increases our damping. So you'll see here that our damping ratio has gone up similar to what our roll stiffness has gone up. Generally, when you're moving shock positions, there's no need to adjust your shock oil or anything of that nature. It's a fairly small change here. You can see it's less than 5%. If we lay it down to the lowest position, again we've got about the same amount of change. So changing your shock position is a fairly small change to damping. Generally not going to require you to make adjustments to your oil. If you start changing the lower position and the upper position, let's change upper and lower. So moving this inward, we've softened the suspension up, so let's go as soft as we can. So now you can see that by moving it inboard and laying it down, that we have almost a 10% change in our damping ratio. So under these conditions, you probably want to start thinking about making an shock oil change as well. Okay, let's look at what happens when we make spring rate changes. Let's just go back and reset everything back to where it was. So let's make some spring rate changes. So right now, this is set up with the hardest spring that we have in our toolbox. So let's go to the softest spring we have. So there we've gone from hardest to softest, and we're only about 6% difference in our damping ratio. So it hasn't made a huge difference. We've gone, significant, well, not significantly, we've gone a little bit softer in spring rate, and our damping ratio, because our spring is now softer, has gone up. So in that condition, could you adjust your oil? Possibly. Would it make a really noticeable difference in handling? Not likely. So springs depends on how much of a spring rate change you're making, but generally your shock is going to have a fairly wide range of spring rates that it can handle, and still control the chassis. So if you want to make large changes to your damping, then what you're going to want to get into doing is changing either shock oil or your pistons. So if let's go back to our basic again. Oops, just made a boo-boo. Save instead of resetting. Okay, so now let's just click through some different piston hole configuration. So we've got a 6x1.46 here. So going to that, we're going to make our damping significantly less. So making these kind of changes, you're looking at making a significant change in the handling. You're going from a very bumpy track to a very smooth track, or big jumps to small jumps, something of that nature. So we can just click through a bunch of different ones here. So this one here, we have significantly higher damping. So this is something that you might want to consider running on a very bumpy track, or a track that has very large jumps and you don't want to be bottoming out coming off the jumps. So this one, very low damping, probably not something that you're going to run. Again, normal damping, we go down to the bottom here. This one's very low damping. And last but not least, fairly normal damping again. So you can see here quite easily, you can click through, you can enter various different piston hole numbers and diameters of holes in the chassis manager, which we'll show you in a few minutes. So that's the other big thing here that we can do. Like, let's go to one of these ones that's really soft. So there's a 6x1.74. So we're at a damping ratio of 0.4. For an off-road vehicle, you're probably going to want to start with the damping ratio in the 0.9 to 1.1 range, or somewhere in that value. So to get this up to that sort of range, we're going to have to make a very significant change to our shock oil. So let's try going to 1200 CST. Still not there. So let's go to 2000. Even not there yet. 2200. Okay, we're getting close. So you can see that, if you've got a very, very low damping ratio, you're going to have to make major changes to your shock oil in order to get it up into something that's going to work. If you were to just swap from this piston, let's go back and reset again. So if we were to go from this piston at 0.94 and say, okay, well, let's try 6x1.74. You would go out on the track without changing oil or anything, and the truggy would be wallowing around like 63 caddy. It'd just be very unresponsive, very boingy. It's not going to be a good situation. Okay, so let's let's move on to our damping ratio tab, and let's still want to leave, and let's just look at our damping ratio tab. Okay, so on the damping ratio tab, what we can do is we can compare different pistons. We can look at the effect of different viscosities, temperatures, wheel velocity ranges. So let's just graph something here so we can show you what this is all about. So let's select the first two in the list here. So, and you can just, if you want to select more pistons, you just control click and you can select as many as you want. Likely not going to want to have too many because the graphs get cluttered pretty quickly. So I've got my viscosity range set to 500 to 600 and just an increment of 100. So we're just going to look at two oil viscosities for these two pistons at 20 degrees centigrade. And the wheel velocity range, this is not how fast the vehicle's going, this is how fast the wheel is moving up or down. So let's just graph that. So there we can see our graph now. So on the vertical axis here, the y-axis, we've got our damping ratio, which we've already explained, and on the x-axis we've got the wheel velocity. So there you can see our 6 by 1.46 are the first two, the bottom two here at 500 and 600, and then we've got our 8 by 1.26 at 500 and 600. So the 6146 is the lowest damping, and you can see the curves here are fairly similar. They're parallel more or less to each other. There is a slight change in the slope of these curves, but it's fairly minor because these are fairly similar piston configurations. Now, one thing that we can look at with this as well is what happens when you have a number of different pistons that have the same total hole area. So what I mean by that is if you calculate the total area for 8 holes that are 1.26 in diameter and compare it to 6 holes by 1.46 diameter and the areas are equal, let's see what happens when we do that. So the three that we've got here, we've got 3 by 1.74, 4 by 1.54, and 5 by 1.35. Okay, all three of these are fairly similar hole areas. They're not exactly identical, but they're fairly close. So it can show us something by looking at this. So let's just change this to 600. So now we're only going to look at one viscosity value. So there you can see that the 3 by 1.74 has the lowest damping and the 5 by 1.35 has the highest, even though these have the same total area. So the key thing to realize here is that smaller holes are it's gonna take more pressure, more force to move that fluid through smaller holes than it will through moving the fluid through bigger holes. So the rule of thumb here is for equal viscosity, that's the other key point here, if we're looking at the same viscosity oil, at equal areas, so that if you want to play around with making your own pistons and drilling holes, the piston that has the smallest holes will produce the highest damping. The other thing at this stage I should probably show is if there is a piston configuration in here that you want to look at and you want to try something, you can add pistons. So let's just go and we're just going to open up the chassis manager and go to the shock tab, and we're just going to add a piston here. So let's add a 2-hole by 2.0 millimeter. So we're going to have 2 holes, 2.0, oops, 2.0, piston diameter will be the same, and piston thickness will be the same. So we want to add this so we can put it on either the front or the rear. So check this little box, and that'll automatically add this piston to the selection available for the rear shock as well. And then just click Save. And close this out. Let's go back to the damping tab. And now you can see we've got a 2 by 2.0. So let's just click on that, and let's go with our bunch of graphs there. So you can see there we've added this in. This is a different area than these other 3, so it's not really directly comparing to what I was talking about. But I just want to show you how easy it is to add different pistons and see what the effect of different hole sizes and configurations is. So the important thing to realize here is that this graph is showing wheel velocity. So this is increasing wheel velocity, and this is your damping ratio on this axis. So the handling range, or the range that we're looking at on the setup tab, this value here is down at the bottom end. So we're probably in the 200 to 300 wheel velocity range. Once you start getting out into this upper region, this is the kind of velocities, wheel velocities, that you will see when you're landing off jumps. And they occur very quickly, but you do need to be aware of what your damping is doing at higher velocities. Looking at it at just one point is great for getting a sense of what it's going to do to handling, but when you're running an off-road vehicle, you've got a lot more than handling to deal with. You got jumps and bumps and all that sort of stuff. So this gives you an indication of what you can expect when you're landing off jumps. Okay, let's look at something else I want to point out here. The other important thing that you need to realize is how the damping ratio changes depending on the hole configuration. So let's look at, these are not going to be the same area. These are 2 different piston configurations with 2 different areas. So we're going to look at the 3 by 1.74 and the 10 by 1.14. So let's graph these. So now you can see I've got a fairly different curve here for the 10 by 1.14 versus the 3 by 1.74. There's a much steeper slope on the damping curve as the velocity of the piston, or velocity of the wheel, increases. So we're getting more damping change from our low speed area down here to our high speed area landing over jumps, which is actually over this whole big area here. So we can use that to our advantage as well. So let's see what we can do, like up here at the high end. Right now we've got almost identical damping once we get out to the very high velocity. Let's say, for example, we're happy with the way the vehicle handles at low speed, so we want to try and maintain that, but we need more damping, more pack at the higher speed range when we're landing off jumps. So let's graph this. So now you can see here we've got these 2 lines. We've got the red and the yellow line. The red line being the 10 by 1.14 and the yellow line being the 3 by 174. So the 10.114 is at 500 CST, and the 3 by 174 is at 600. So you can see we've got quite a difference in the damping at high speed, but down at low speed here we've got almost identical damping. So in theory, this should, if you built up pistons or built up shocks with these two different configurations, you should see essentially the same handling in the low speed range, but landing off jumps. The 3x1.74 should handle the jumps better and provide more damping at the high speed range. Okay, so let's go back to our setup page and we'll do a comparison here. And I'm going to do a new setup. We'll just call this piston holes. And what I want to set as my default, I'm going to set 10 by 1.14 at 500 CST. So this is the configuration that we're saying we're starting with. So now let's go to the damping tab and click on dynamic response. And so now what you're going to see is some graphs that show essentially the ride height of the chassis above the ground versus the time. So this graphic here shows a step response. So it's essentially a very sharp bump or a very sharp hole. So in this case, we hit a bump and the suspension is compressing, and then we drop into a hole, and then the suspension is rebounding. So you can see here this curve is behaving quite nicely. We've got a little bit of overshoot. It's responding fairly well. So now we want to say, okay, we're going to coming off a jump. So let's look at landing off a medium jump. And we're getting into problems where we're getting just too much deflection. If we go off a large jump, we're actually bottoming out. We're slapping. So we want to try and increase the amount of high-speed damping we have, or pack, and not affect the low speed. So we already looked at the other graph, and we found that if we change to a 3x1.74, let's go back to our step response here. If we go back to a 3x1.74, we should get the same response. Well, we don't quite have it here, and that's because we didn't change the oil viscosity. So we needed to go to 600 weight oil, and now you can see the response is almost identical. So this is what you would consider low speed. If you want to look at the velocities here, so we're at a wheel velocity of around 200 millimeters per second, which in this case here is down in this range. Okay, so let's go back to displacement. So if we maintain the same sort of response in the handling range, now let's see what this has done to our landing off a jump. So now you can see our current setup, which is the blue line, is getting much more displacement than our red line here, which is our new setup. So what we've done is we've managed to affect only the high speed range and not the low speed range. So something that's that you can use when you're playing around with the program to investigate different configurations, which is a lot faster and easier than sitting at the track trying to rebuild shocks and change oils and change pistons and not really know what's going to happen. So this can really shorten up your tuning time if you get familiar with this. Okay, so I think that's all I want to talk about at this point. We're running a little bit long here already, so we'll save some more stuff for our next episode. The important things to take away from this is air temperature changes of 10 degrees C. You're going to need to make 100 to 150 CST change in oil viscosity, depending which direction the air temperature goes. You'll either have to increase it if the temperature goes up, or you'll have to decrease your viscosity if the temperature goes down. The other thing that we talked about was equal total hole area at same viscosity. The smaller holes will produce more damping, and the easy way to remember this is it's harder to force the oil through smaller holes than it is to force it through larger holes. And lastly, as the shock velocity increases, a piston with fewer larger holes will have a greater increase in damping, or a greater change in damping from low speed to high speed. so which translates to more pack, as the off-road gang call it. Okay, that's it. Up next, we're probably going to do some more investigation into shocks, because there's lots of stuff to cover here. Okay, so see you next time.